Good evening. So I'll be presenting our paper titled SelfTune, Tuning Cluster Managers. This is in collaboration with various folks when I was working at Microsoft Research. So large-scale cloud providers often rely on cluster management frameworks for their operation. So these cluster managers perform a variety of essential functions like job scheduling, container allocation, VM provisioning, resource auto-scaling, and so on. And given the scale at which these cluster managers operate, they often have a large impact on the effectiveness and efficiency of the end-to-end system that they are a part of. And some examples of cluster managers include Kubernetes, Azure Protean, Google's Borg, Facebook's Stony. And so one aspect of cluster managers that is worth noting for our discussion is their iterative nature, where they go through a cycle of measuring the health of the cluster and then changing its state accordingly. One such cluster manager that we consider in detail is the Exchange Online Workload Manager at Microsoft. It schedules background jobs on Substrate machines. So Substrate is a data management engine which runs on several 100,000 servers and manages billions of data items. The kind of background jobs that run are the ones which are of the more schedulable variety, where they can afford some delays in execution, like data analytics, data fragmentation, and we want to schedule these jobs in a way so as to maximize resource utilization and to maximize throughput. Now, some of the health metrics that are measured in this case are CPU utilization, disk latency, network ping losses, and using these, the workload manager adjusts the resource concurrency for different resources. That is, it limits the number of jobs that can simultaneously access a resource. And now the heuristic that governs this operation of how the state should change depending on the health of the resource is fairly involved. And in fact, it is dependent on hundreds of configuration parameters. And there are different configuration parameters depending on the resource type or the job priority and also geographical scale. Another cluster manager that we consider is Kubernetes. It's a well-known container deployment and management system. Here, the health metrics that are measured are like CPU and memory utilization, the number of pod evictions. And these are used to make decisions about whether you want to deploy new containers or whether you want to resize existing ones. And once again, you have a large number of configuration parameters that govern this behavior. For example, here is a snapshot of a configuration file from the Kubernetes repo. In particular, it's the vertical pod autoscaler. So you have like these many configuration parameters. So the takeaway is this situation is not uncommon, and there are often a large number of these. So configuring them well can have a large impact, and it's very crucial. So oftentimes, these parameters are set through a combination of domain expertise and limited empirical evaluations, due to which they can be suboptimal. The other issue we see is they're often global and static, and this can create suboptimality along both the temporal and spatial axis. That is, a configuration that works well for one cluster may not work for another, and a configuration that works well today may not work well next week, because oftentimes the environments in which these cluster managers operate are very dynamic. So you can have drifts in like workload patterns, and oftentimes hardware is replaced or upgraded. So for instance, an example of temporal issues is this was like posted in the GitHub repo of Kubernetes, where a user said that they found a configuration that worked well on weekdays, but on weekends, it adapted too quickly to certain changes in workloads, because of which it underestimated the workload at the beginning of the next day. So, and here they said that they're okay with compromising some wastage of resources in anticipation of better parameters at the beginning of the next week. So what are the options that are available now? One is you can create and manage multiple configurations for different environments. But the problem is this takes a lot of manual effort, so it's not scalable. And it also doesn't solve the suboptimality along the temporal axis. The other is there are a number of learning-based frameworks that have sprung up in the last several years, like Cherrypick, bestconfig, Metis, and so on. But the algorithms that they use, like Bayesian optimization or branch and bound, each of them suffer from different issues, like either assuming a fixed function or working well only for smaller dimensional problems, or like making some assumptions about the prior. And some of these also have a non-trivial amount of engineering overhead. And I think it's, when the goal is to build a practical system, this is an important consideration. And this is why we sort of worked on coming up with our own framework. Our framework is called SelfTune. And before I explain the framework in detail, here is a quick example of how integrating SelfTune would look like into Kubernetes. So let's say we want to configure the amount of memory that must be assigned to a container. It's a two-step process. So first, we ask SelfTune for the values to set for these parameters by calling predict. And then you reconfigure Kubernetes with these parameters. And then now the user has to decide what they care about in the system. So let's say they care about reducing the number of pod evictions. So you compute the number of pod evictions you have in a certain time scale, and you call SelfTune saying, this is the reward, and this is what I want you to minimize. And over time, the SelfTune will return better parameters. A takeaway here is that all the user needs to decide is what they care about ultimately in the system, and figure out a way to compute it. So here's the framework in detail. SelfTune consists of both an API and a learning engine. As I mentioned before, the cluster manager is minimally modified to include the API, and the learning engine is fairly small, so it can either be included with the client API or be deployed separately. And coming back to the iterative nature of cluster managers, we note that it is similar to the classic RL setting, where we observe health, deploy some action, and repeat this process. So a simple but crucial insight is that SelfTune can piggyback onto the setup to tune its configuration parameters. So this is important because it saves the engineering overhead of having to set up a new data flow loop, or having to change the architecture of an already complex system just to incorporate a tuning framework. So to sort of summarize how a single round of learning using SelfTune would look, the cluster manager asks the learning engine for the value to use through predict. The learning engine returns the decisions based on some strategy. Then the cluster manager changes state based on these new parameters. Finally, it measures health of the system and passes it on to the learning engine through set reward. And this process repeats naturally, and over time the learning engine returns better parameters. Here are some of the key features of SelfTune. First, it introduces almost zero engineering overhead. And when I say engineering, I mean both in terms of the integration effort and in terms of the computational overhead due to the lightweight algorithm that it uses. And it operates on the idea of implicit context, where a user can choose the granularity at which they want their parameters to be tuned. That is, whether you want one parameter per machine, or one for every cluster, or whether you want application level or workload level tuning. The other is the underlying algorithm that I'll talk about later makes minimal assumptions about the structure of the learning task. So one question that may come up is, okay, since we've established that this is similar to the RL setting, why not use a traditional RL frameworks or algorithms? So we've noticed a bunch of issues with these. First is, when you're using a traditional RL algorithm, it depends on the state space. So you need a representation of the state space, and this can require handcrafted feature engineering. There are some algorithms, there are some frameworks which try to sidestep these by learning the features itself, but that again increases the sample complexity. And there are some other algorithms which only work for categorical parameters. Two more key considerations that arise due to the fact that environments vary with time is this necessitates online tuning of parameters rather than offline tuning, where you can collect data, train your algorithm, and then deploy it. Here you want to constantly adapt to changes. And you want your sample complexity to be small, which is the number of rounds it takes for your algorithm to keep up with an environment. So because of these two, the Bayesian optimization, which is the go-to algorithm in systems literature, is not ideal for our setting. So we instead use a simple and intuitive algorithm for continuous bandits based on some work in recent times. And this forms the basis of our learning engine. So moving on to evaluation, we consider three cluster management settings. One is Kubernetes, where we simulate a social networking application that uses about 30 microservices using the Death Star benchmark. and our goal is to minimize tail latency here. So here as you can see highlighted, we compute the P95 latency and pass this on to SelfTune through set reward, and we use that to tune about 100 parameters, both real valued and discrete. And here are the results. So we compare SelfTune with Bayesian optimization and epsilon greedy, which is a variant of an RL algorithm, and default is just the default configuration. The first row is the final tail latency that we obtain. So the value for SelfTune is slightly smaller than the others, but the more important thing is the number of samples it needs to reach this value is considerably smaller than the other methods, that is 8 versus 30 or 40. The other metric we look at is iteration cost, which is obtained from as the algorithm progresses, it tries out different configuration parameters due to which it has like a distribution of latencies that it incurs. So we can compute different percentiles for these latencies. And we see that SelfTune has a considerably smaller iteration cost than these other algorithms. We also note that for P95, the other algorithms have a very large iteration cost, which means there are some cases where these algorithms try very bad parameters. But in general, we've ensured fairness by starting all of these algorithms from the same starting point. The other evaluation setting we consider is the Exchange Online Workload Manager, which I spoke about in the beginning. So here, our goal is to optimize resource utilization and throughput. And we have results from a few months of deployment in various forests. Here we compute two metrics for the health. One is a grant ratio, which is a proxy for throughput, and HUP, which is a proxy for resource utilization. And using these, the workload manager controls the resource concurrency. And the workload is live production scheduling workloads, and the implicit context we use is machine level tuning. So you have different parameters for each machine. And here are the results. So we try with both of these rewards, that is throughput as the reward and resource utilization as the reward. So the first two clusters with throughput as the reward, we again look at both of these metrics again, which is throughput and resource utilization. We see that when we are using throughput as the reward, there is an at least 25% increase in throughput, and as much as like more than 100% in some cases. SI denotes statistically insignificant. So resource utilization hasn't changed, but it's good to know that it hasn't regressed. In the third cluster, we use resource utilization as the reward, and we find a 1 to 3% increase in resource utilization, while simultaneously observing a 15 to 20% increase in throughput. The third setting that we consider is Azure Functions, which is like a Functions-as-a-Service platform. So Functions-as-a-Service is what you obtain when you naturally progress from like bare metal to VMs to containers. So in Functions-as-a-Service, the unit of deployment that you have is function, which is like much smaller than the other cases. And here the problem is of the trade-off between cold starts and wasted memory. So let's say a user makes a request for executing a function, and let's say you do not have that function already loaded into memory, then there'll be a cold start, and because of which the end user latency is affected. The alternative is to always keep this function in memory. But the problem is the end user latency is minimized, but you're wasting a lot of memory. So we want to stay in the bottom left corner of this graph. That's the ideal state. So some of the previous works sort of tackle this problem by parameterizing it using two configurations. One is pre-warm and the other is keep alive. So the general idea is you load a function into memory in anticipation of an execution. So you try to anticipate when an execution is going to happen and load it into memory. So that is pre-warm is how long you wait since the last invocation before you load into memory, and keep alive is once you load into memory, how long you keep it there. A recent work decides these two parameters based on a histogram policy, where it computes the histogram of idle times and uses and sets pre-warm to a small percentile and keep alive to a larger percentile. And we found that this actually works really well, and this is a good global configuration. So in this case, we wanted to use SelfTune to see if we can apply more fine-grained tuning, like in this specific case, application level tuning. Can it further improve the performance? So that's what we do. So here, the health metrics that are measured are memory utilization and cold starts. And these are used to make decisions about when to load and evict functions. And here the reward that we use is, that is like we want to minimize memory utilization. so memory wastage. Yeah, so the parameters are pre-warn and keep alive. The workload is real Azure function traces that we use, and the implicit context is application level tuning. So the setup is we start off with finding a Pareto optimal boundary using grid search, and then we use these as starting points for SelfTune and see if SelfTune can sort of further bring down this boundary. And so on the right side, I'm just expanding this section of the graph on the left. So the circles are these pre-configured configurations, and these are the starting points for SelfTune, and the crosses are the configurations that SelfTune arrives at. And we see that in most of these cases, there is a 10 to 12% reduction in memory wastage for an insignificant increase in the cold start percentage, which is very encouraging, and sort of proves the proves that like application level tuning can really help. And that's about it. So the summary is we come up with a framework for tuning configurations in cluster managers with minimal engineering overhead, and it uses online tuning with small sample complexity, and it's versatile in the sense that you can decide the granularity at which you want to tune because of the very little computational overhead. And we've also demonstrated success on production workloads. Yeah, I'm happy to answer any questions.